Okay, so we're going to continue with section 7.7 this morning over hyperbolic functions. Um, the two basic hyperbolic functions were the hyperbolic sine and the hyperbolic cosine, and they have this slightly unusual definition. Looking at the formula for hyperbolic sine, it's not entirely clear why we would call it a sine function, or why we would call this a cosine function. But these do end up working quite similarly, as we saw in the derivatives last time, and also in the way that we define all of the other hyperbolic functions, like hyperbolic tangent is sinh over cosh, and hyperbolic secant is 1 over hyperbolic cosine. So all of these definitions work the same way that like tangent is defined in terms of sine and cosine. Maybe we could also switch back over to the graphing tool. Find my tab. Maybe take another look at the two basic hyperbolic functions, sine or sinh and cosh. This is what they look like close to the origin. So sinh is somewhat analogous to the x cubed function. You can see how it kind of flattens near 0 and then continues on up towards positive infinity, except it's not x cubed because it never actually flattens. X cubed actually has a horizontal, not asymptote, horizontal tangent line at the origin, so this is different. And also, cosh looks somewhat similar to an x squared function, or maybe an x squared plus 1, because it has this shape where we're going to infinity, but this is actually much, much steeper than an x squared function. And if you zoom out even a little bit, you can see this. So if you want to go out even just, where is this, about 5, you can see that it's already off the graph up here over 70. And if you zoom out even further, both of the curves for sinh and cosh look almost vertical. And that's because they're defined using these exponential functions, and as we know, exponential functions get really large really fast. Okay, so that's an overview. We also had some identities that you might find helpful on the homework to do some of the integrals or derivatives. Which brings us to the derivatives themselves. We found the derivative of sinh to be cosh and the derivative of cosh to be sinh. So this is another similarity between the hyperbolic functions and the trigonometric functions. But there are some subtle differences, like the derivative of cosine is negative sine, but the derivative of cosh is positive sinh. So they're similar, but there are these differences that you have to remember, like this minus sign here on the derivative of hyperbolic secant. Okay, and this is where we stopped last time, and where we're going to pick up this morning is with actual examples, finding derivatives, and then we're going to do some integrals as well. So we'll start with this one. We're going to find the derivative of hyperbolic secant with the square root function inside of it, the square root of 1 minus, or excuse me, the square root of 1 plus x squared. So since we have a function inside of the hyperbolic secant, this is going to be a chain rule problem. So we need the outer derivative of the hyperbolic secant. That's this rule up here. So we get a negative sech, and then we leave the inside alone. So that means there's going to be a square root of 1 plus x squared inside of our hyperbolic secant. And we also need a hyperbolic tangent, with the square root inside, square root of 1 plus x squared. And then we need the derivative of the inner function of the square root of 1 plus x squared. So someone tell me, what is this inner derivative? What is the derivative of the square root of 1 plus x squared to finish off this problem? So remember, a square root is the same as a half power. Like this.
So x over square root 1 plus x squared.
Good. Yeah, so you decrease the power by 1, and that gives you a negative a half, so you can flip it to the denominator. Good. Let me write out this first part, and then I can start writing the derivative of the inner function. So the square root flips to the denominator, and then you get an x on top. Because we have to do an inner derivative as well. You'll multiply by a half, and then the inner derivative is 2x. So the half and the 2 from the inside cancel, leaving you with just an x. Good. Any questions over that example? Okay, so this first part involving the hyperbolic functions, this is the new part of the problem. Taking this derivative should be something that you guys are familiar with, I hope. Okay, so one more example. This one is x times sinh of 3x. And we're taking the derivative, of course, still. And this is a problem that combines a product rule, because we have x times sinh, and a chain rule, because we have 3x inside of the sinh function. Okay, so we need the product and chain rules. So the product rule tells us to take the derivative of the first function, and maybe I'll just write it out as the derivative of x. And then you multiply by the second function, so that's sinh of 3x. And then you add the first function times the derivative of the second, and that'll be sinh of 3x in this problem. So the first part is easy. We know the derivative of x is 1. So all that's left here from the first term is sinh of 3x. And then we just have to deal with this derivative here. So the derivative of sinh, and remember this is the chain rule part of the problem, the derivative of sinh is one of these rules that we learned. It's just the cosh function, hyperbolic cosine. So we'll come back down to our example, and we'll write that the outer derivative is cosh, and then we leave the inside alone. What's the inner derivative of 3x? It's 3, right? Okay, and that's it. This is the whole derivative. If you were wanting to clean it up, you could uh, combine the x and the 3 and move them to the front. And this would be the cleaner way of writing things. So you have your sinh of 3x plus 3x times cosh of 3x. Writing it this way just lets the person who's reading it know what's plugged inside of the cosh function a little bit easier. You could accomplish the same thing by writing parentheses here for clarity. Any questions over the second derivative example? Okay, so if there aren't any questions, we will move on. Oops, grab too many pages there. We will move on to the integrals. So anytime we have a derivative rule, we can reverse the rule to get an integral rule. So that means the integral of sinh is going to be cosh. And since I have an indefinite integral, remember to always add a constant. And then the integral of cosh reverses the rule for sinh, so we get a sinh x plus c. What's this integral for sec squared of x? Anyone? If you look back to your list, you can tell what it should be. This one is the tangent, hyperbolic tangent. Oops. Of course, the n should come before the h. Okay. And then this one was the hyperbolic cotangent, but it had a minus sign in the derivative, so it'll go here on the right side in the integral rule. This one came from the hyperbolic secant, and it too had a negative in its rule, so it'll move over to the right side. And then here we have hyperbolic cosecant, and again we need a minus sign. Okay, and as I said, these rules are totally analogous to the derivative rules. They're just written in the opposite order. So here we have the derivative is equal to something, and then this just reverses it. So the derivative is essentially here, and the original function is here on the right. Okay, so let's go ahead and try applying those. What about this one? Hyperbolic tangent of 8x. Let's go up to our rules and see if one of them applies. So do we see a rule for hyperbolic tangent here? Well, no. That's sinh, cosh, secant squared, cosec squared, and then these involve two different functions. So we're going to have to be a little bit creative in this example. And we're going to do the same kind of thing that we did to integrate the tangent function. We're going to rewrite hyperbolic tangent as hyperbolic sine over hyperbolic cosine. So this is sinh of 8x over cosh of 8x. Okay, and what we did, let's see, which section was this? I guess when we were learning about the logarithm, that's where we learned how to integrate tangent. What we did was we did a u substitution for the denominator. So in this case, u would be cosh of 8x. And then we need a du. What's the derivative of cosh? Anyone? Anyone want to tell me?
Is it sinh x?
Yes, that's exactly right. And thank you for remembering that this one does not get a minus sign. So that's the difference between hyperbolic cosine and the regular cosine. You don't get a minus sign when you take this derivative. But for this one, we do have an 8x on the inside. So we need to take that inner derivative and we get a constant multiple of 8. And then we tag a dx on the end. So we have a sinh of 8x here, and of course we need a dx, which I neglected to write a second ago. So the sinh 8x dx becomes a du over 8. So we can just divide through by 8 on both sides, like this. So with our u substitution, we're now looking at a, well, we can either write the 1 over 8 on the inside or in front, and then we have a du over u. What is this integral of du over u? It's one of the rules that we learned before the first exam. Anyone? No one wants to volunteer. Okay, so make sure you remember all of these rules from earlier in the semester because we're still going to be using them. Du over u, when you take its integral, becomes a logarithm, a natural logarithm. And I'm going to go ahead and write the u as hyperbolic cosine of 8x plus c. And remember, these absolute values need to be there because we can't take natural logarithms of negative numbers. That's essentially the reason. Any questions over that first integral example? Okay, so here's another integral, number 2. We have a cosh squared of x. And again, you'll want to look back up to your rules, your basic integral rules for hyperbolic functions, and you'll see that, well, cosh squared is not up here. So we're going to have to do something else that's maybe a little bit creative. And if you think back to the identities that I told you about that might come in handy, you'll see that number 4 has cosh squared on the left side. And this is what we're going to use in order to actually complete this integral. We're going to rewrite cosh squared as cosh of 2x plus 1 over 2. And we will be able to find the integral of the right side much easier. Maybe I'll write that rule down here. that we're using. So use the fact that cosh squared of x is equal to cosh of 2x plus 1 over 2. And then for this integral, since we have one function plus another thing, we're going to want to break this up into pieces and probably move this constant to the front. So here we have over 2 for the inside. Let's move that 1/2 to the front. And then we can see that we have a cosh of 2x that we need to find an antiderivative for, and also the constant 1. This one we'll have to do a small u substitution for, since we have a 2x inside of the cosh function. So we'll pick u is equal to 2x, and then du would be 2 dx. So you'll want to move that 2 over here to the left. So when we do our integral, we'll pick up an extra constant, an extra 1/2. So we have a 1/2 on the front, and this one will pick up an extra 1/2. And then we need the integral of cosh, which is sinh. Leave the inside alone. Oops, that should be a 2x, of course. And then the integral of 1 will get an x, and then add your constant on the very end. Okay, so we could have added a little bit more detail to our work here. So remember what we're doing is we're saying that cosh of 2x is the same as cosh of u, and then we have a 1/2 du, or a du over 2. So this is the substitution that's going on here. But once you get enough practice at u substitutions, you might not have to write out all of it on your paper when you're working. So sometimes you can make things go a little bit faster. Any questions? No? Okay. So let's do one more integral example before we talk about inverse functions for the hyperbolic functions. So here we have the integral from 0 to the natural log of 3 of 4e to the x power times sinh of x dx. So this problem you definitely won't find a simple rule for up here. We're going to have to do a bit of extra work in order to deal with that extra exponential function in the front. So for this problem, instead of trying to do something like before, where we rewrote tangent or we used one of our identities, for this one, we're going to have to go back to what the sinh function actually means. So remember, way back on page 1, or last Friday, we learned that sinh is e to the x minus e to the minus x over 2. And this is what we're going to have to use. So replace your hyperbolic sign with e to the x minus e to the minus x over 2, like so. And then we're going to distribute e to the x into the parentheses here. And we'll probably pull this half outside to simplify things. So we still have an integral from 0 to log 3. If we pull the half out and use it to simplify with the 4, we'll get a 2. And then we'll distribute the e to the x inside. So this comes out, e to the x goes in. When you multiply e to the x times e to the x, you get e to the 2x. Remember, you add the exponents when you have the same base. And when we multiply by e to the minus x, x minus x gives us a 0. And e to the 0 is just 1. So rewriting this function sench using its original definition actually helps us simplify this third integral problem, because we know how to integrate exponential functions, and we know how to integrate something like 1 using the good old power rule. Okay, so the 2 goes along for the ride, and then from this first function, e to the 2x, once again, this might be something you can do in your head, or if you want to write out the details, we have to think about the 2x as being an inner function. So this is kind of a U substitution rule problem. But the crux of it is that we pick up a 1/2 when we integrate. And then we get a minus x from the 1. And we can rewrite our limits of integration over here on the right with our vertical slash notation. Any questions over that step? Like the U substitution in particular? No questions? Okay. So you'll probably want to distribute this 2 to help simplify. It'll cancel off the half, and then you can just write the minus 2x over here before we substitute in our limits of integration. So go ahead and write in natural log of 3 for x. And then we'll subtract and plug in 0. We'll get an e to the 0 minus 2 times 0.
0 minus 2 times 0
Okay.
is 0.
And then my echo dot might have interjected there. I'm not sure if you could hear that. It was in the other room. Okay, so first of all, we need to do a little bit of simplification. This is the correct answer, but there's some simplification that we really should do. Here in this exponent, we have 2 times the natural log of 3. What we want to do is use one of the exponential or logarithmic rules, really, and move this 2 to an exponent on the inside. So we're really looking at the natural log of e to the natural log of 9. And that'll simplify and just give you the number 9, which is nice. And then you have the minus 2 log 3. And then from over here, there's a minus 1 from e to the 0. And then there's one one more simplification step we can take, 9 minus 1, to give us 8 minus 2 log 3. And that'll be our final answer there. Any questions over our third integral example? Okay, so then let's just move right along then to the inverse functions. We're not going to spend quite as long, or not nearly as long, talking about these inverse hyperbolic functions as we did the inverse trigonometric functions. We've kind of had some practice with inverse functions now, so we're going to leave off a bit of the details. But the issue here is that, well, just looking at sinh, the issue is that this is a one-to-one function. You might remember from its graph that it looks something like the x cubed function, which is also one-to-one, passes the horizontal line test. So the sinh function is going to have an inverse function, which we'll call, well, just sinh inverse, written like this, using the inverse notation. And if we wanted to spend some time doing it, we could work through the details of finding domains and range for each of the hyperbolic functions and then finding their inverses, just like we did for the trig functions. And then maybe we can switch over to the graphing tool and just take a quick look at what a few of these look like. And then zoom back in. Okay, so here is sinh graphed in red. Let's see. Can we get the inverse function here? Yes. There is sinh inverse graphed in green. And you remember the way that you can get the graphs of an inverse function is by looking at the reflection of your original function across the line y equals x. So you interchange the x and the y values to go from the red function to the inverse function in green. Let's see, and it's possible, let's see, so on your, if you use this Desmos on your homework or something, you can find the hyperbolic functions here on the menu. It doesn't look like they have a button for the inverse functions, but we can just type in the inverse on our keyboards. Yeah, and that's not there either. Okay. So maybe we can clear those two out of the way, get rid of the keyboard, and maybe look at cosh. So cosh hyperbolic cosine is not one-to-one. That means that we would have to do a little bit of work finding the domain of cosine inverse. So let's take a look at what Desmos gives us. And you can see that what it's done is split the function in two here about the y-axis, and then it's taken the the positive part where x is positive as our domain, and then to get the inverse you mirror across the line y equals x to get the red graph. And like I said, we could do this in more detail, and we could look at all of the hyperbolic functions, but we're going to leave that off because, well, we've done a little bit of that with the trig functions, and really we're not so much interested in the geometry of the hyperbolic functions, what the graphs look like. The reason why we're even talking about hyperbolic functions is because they're actually an important source of new integrals. So they give us some new integral rules that we're about to talk about. So we're not going to spend much time talking about their derivatives or their graphs. We're just going to look at some integral formulas that we get from them. And if you want to see a few more of the details about how this works, your textbook does include quite a bit of it, but it would take a lot of time, a lot of class time to work through all of those details. The important things are these 6 new integral rules that we're about to see. And they look a lot like the rules that we learned for the inverse trig functions, with a few important details that are different. Like this one, you might remember seeing a similar rule for an integral that looks like this, except there was a minus sign in between. And if you have a plus sign, this is no longer an arc sine, it's actually an inverse sinh. Let's see, and then there are a few details that I'm going to include, but we're not going to talk in detail about why they're here. I just need, in this rule, to make sure the constant is positive. And then the next rule, we're going to switch the order here and then put a minus sign in between. So we're going to get square root of u squared minus a squared, which again looks like the arc sine rule, but with some differences. And this one is inverse cosh, hyperbolic cosine. And we'll get a u over a on the inside plus c. And then the detail that I need to include that most of the time you won't have to worry about is this inequality. A needs to be positive and u should be bigger than a so that you're not trying to either divide by 0 or take a square root of a negative number. And that's why we have this. The next rule looks a bit like the rule for arc tangent. Remember, we had an a squared plus u squared in the denominator. For this rule, we're going to have an a squared minus u squared. And this one is a little bit more complicated. It could be inverse tanh or cotangent, hyperbolic tangent or hyperbolic cotangent, depending on, well, I might run out of room, but I'll maybe write it below here. So it could be this one, inverse hyperbolic tangent, or it could be this one, inverse hyperbolic cotangent. And then I should have left myself more room. The first rule applies when u squared is less than a squared. And the second rule, this lower part, applies when u squared is greater than a squared. I see what the problem is here. We actually only have 5 rules. This shouldn't be here at all. Okay. And then 4 and 5 look like the rules for arcsecant. This one is u times the square root of a squared minus u squared, which reverses the rule for hyperbolic secant. And here's what we get, a minus 1 over a, and then the inverse. I think I said it reverses the rule for hyperbolic secant. It reverses the rule for arcsecant. Of course. We all remember what that one looks like, I hope. Yep. So very similar to arcsecant, except this one has the order reversed here under the square root. And for this one, again, we have to make sure we're not dividing by 0 or an imaginary number. So u needs to be positive, and a needs to be larger than u. And now the last rule, we'll put a plus sign in between a squared and u squared. And this one is the hyperbolic cosecant. And we don't have to worry about negative numbers under a square root or zeros. Well, I guess we do have to worry about 0. So at least one of these two needs to be bigger than 0 for this particular rule. So a should be bigger than 0. Okay, any questions over the rules themselves? And once again, we didn't go through the details of why these work, and that's because they're very similar to the hyperbolic, they're very similar to the inverse trig functions that we learned about in the last section. And if you do want to learn about the details about why these work and how they work, you should take a look at your textbook, because it does work through a lot of the details. Or if you wanted to ask me questions about them, of course, we can talk about those. Like I said before writing down the new rules, is that really our primary purpose here of learning about these functions is to be able to do more integrals, like this one, which is not a problem that we could have done before learning these new rules, because the order here is switched from the arc sine rule that we learned in the last section. This one is actually going to be, let's see, I set those aside. This is going to be like this rule. I pointed to the wrong one. This rule here, where we have a function squared minus a constant squared. So it's a cosh, a hyperbolic cosine. Okay, let's get some of those papers back out of the way. So we have to identify the constant and the function. So a squared is going to be 3. And then the u squared comes from the first guy, 2x squared. And we know both of these should be positive. A and U should need to be positive. So A is going to be the positive square root of 3. And U should be the square root of 2x, the square root of 2 times x. Okay. And then once we identify U, we also need du, the derivative of this, of 2, square root of 2 times x, is the square root of 2, and then we tag on dx. Okay. So to rearrange, you would want to move the square root of 2 over here to the left side so that we can just substitute in for dx. Okay. So we can write our du over the square root of 2 on top where dx was, and on the bottom we've identified a squared and u squared. And we know this is going to be an inverse cosh, an inverse hyperbolic cosine. And if you look back to the rule, here we have a u over a on the inside. So let's write that, and then we'll substitute back in to finish off. So remember, a is the square root of 3, and u is the square root of 2x. So that means overall, we have a square root of 2 over 3 times x inside of our inverse cosh function. Okay. And then always remember for an indefinite integral that you'll have to add a constant at the end. Okay, and that brings us right to the end of class, which is perfect timing this morning, because that finishes the section. Do you guys have any questions for me before we leave for the day?